So this fact brings consequences that affects the productivity and the capacity that construction sector has. Apologies. So this fact turns out to put the construction and architecture in the lower position compared to the global industries. So, in architecture, the digitalization has been reflected mainly through the implementation of softwares to design and represent, such as the implementation of building information modeling methodologies and the application of programming interfaces, such as Grasshopper. The evolution of the design softwares, along with the evolution of numerically controlled machines, the CNC machines, have driven the emergence of new digital manufacturing methods in architecture, with more visible impacts on subtractive and additive manufacturing methods through the use of robotic arms. The most versatile robot for use in architecture and construction is the anthropomorphic arm that is represented in this image. This type of robot is basically composed of three parts: the controller, that is the brain of the robot, the manipulator, that is the physical structure of the arm, and the tool, that is the thing that works in the physical stuff. The tools attached to this robotic arm can have direct influence on the function of which robot will use it, and the most common tools and tasks in architecture using this technology are subtractive taskings and milling, additive tasks with extruders, and assembly using grippers. For the control of the robotic arms, in recent years, several plugins for Grasshopper have appeared, with example of KukaPRC and FuRobot, that are two of the best known. The interest in Grasshopper is justified by the articulation that is possible between the architectural design and the fabrication process. Here in school, since the robots that the school have purchased have been late, we use in the first phase a small robot that is the FingerKit Brasio mini robot, and we adapted them to have 6 axes of freedom and try to use the same plugins for Grasshopper that you use to control a normal robot to control this small Arduino robot. To make this happen, we use several plugins for Grasshopper. For example, Firefly to communicate with the Arduino board that controls the servo motors of the small robot. And this is the code that we make in KukaPRC to control that robot and send the information, the values of the axis, to the Arduino board and to the robot. To make a practical application with that robot, that small robot, we make a small structure inspired in that type of structures that are that name is sequential structures, that is characterized as a truss supported by the crossing of wooden beams, and the structure that we have make is that structure. Here is the code in Grasshopper. And this is the final aspect of the idea of the structure. So first we have divided the structure in models. Have these constructors with the goal of finding the center of each of them, and in order to create an orientation plan for the use of the gripper. And this is the final result with the mini robot. We have the simulation and the physical real assembly process. So this is too long a video. I probably it's not okay. So this is the final prototype, scale prototype that we make. So I take the word to yeah.
Hey everyone. Being the last speaker, I promise to be very fast. I think that's the nicest thing I can do. So I just want to talk a little bit about the recent things we've been doing for the last few weeks. And what I'm going to show is not really a research question or a design intent. It was more about finding a way to talk to the robot. So a question of control, because we wanted to have some kind of framework that would allow us to answer to different kind of projects, wide application of exercises in digital fabrication, not just additive manufacturing. So when you start to try to control a robotic arm, you're faced with the question of communication. There's really a problem of language, because it's very easy to be saying tomato and the robot understanding tomato, because you see, unlike G code for 3D printers, which is it's universal. Here we have a proprietary language issue where each robot will have its own language, and you need to tailor your code for that. So as an example, KRC, which is the KUKA robotic language, it's essentially a crystallized list of commands, right? So that's why we call it offline programming. And it consists of a setup. So we have a few variables you have to give it, which tool is it using, the base, and then just a list of commands that it will execute. And for that, of course, no one is going to write that code by hand. There's a few softwares that will come and help you. Most of them have simulation analysis and the code output as a package. They can come as APIs, standalone packages, or plugins. But for us, I think our goal was to bypass this command and obey way of operating the robot through text files, and find another way that could be adaptive and reactive, and also parametric, because I guess we architects work in a parametric environment, and of course you want a parametric way of controlling these robots. So online control will offer you this. It's kind of having a conversation both ways, where the robot will understand new values and you can read values from it in a live setting, and really open up for new applications that offline programming doesn't allow you. So to get into this framework, you really have to ditch commands and accept the world of variables. You can both read and write them as it's operating. And VALACT and POSACT are two good examples, because they host the velocity values and the position values. And in order to communicate, to talk to this robot, you need to follow protocol, of course. In the case of KUKAs, to read a variable, you need to send a bit message that looks a bit funny like this, not a lot of numbers, and then you specify the variable you want to read, and you'll get an answer, X, Y, Z, if you're asking for the position. If you want to have what's happening on the right, where the robot is following a variable that is being changed remotely, you need to build a listener. So it's kind of like, while you work, your velocity is going to be your default velocity plus a value that I'm controlling from my computer. And so I really like workflows. I think it's really nice to share them, and I was happy to see some of them today. And this is kind of the architecture of the workflow we were building here. So in the center, we want to have a main parametric brain that will host different levels of communication. It will focus mainly on geometry and the fabrication strategy. And around it, we'll have nodes for different tasks. But the goal is really to have a flexible template that we can adapt for milling, for cutting, printing, welding, assembly, I mean, whatever comes our way. So for that, for the control the robot in real time, we implemented a client server solution. So we're using Kookavar proxy and JOpenShowVar. We're trying to go fully open source, and I think we are until the very last moment. But it's also something we can replace very easily. And so on this lower level, Kookavar proxy is running on the controller, and it will expose the variables. And JOpenShowVar is running on your computer, and it will pass or read the variables that Kookavar proxy is providing. So of course, in the center we have Grasshopper as the main brain. It's obvious why we chose it. And we have some resources that are hooked up to Grasshopper. Rhino, of course, supports the geometry, and Python as well for the computer power, of course. And also because it allows us to bring in a lot of libraries that we cannot run in Grasshopper, like NetworkX or TensorFlow, sklearn, OpenCV, stuff like that. And then to control external devices, which we kind of needed very soon in the extrusion process here, the first experiments. So we're using Funken, which is a serial protocol toolkit developed by Alexander Stefash, actually from Darmstadt. It essentially will allow Arduino to host a bunch of different functions, and you can just send strings from Grasshopper, and it will actuate on them. And this is the part that is not open source, using KukaPRC. Although yeah, it's something there's, like Antonio was talking about, there's different programs to do this. Also, yesterday we talked about Roche, so it's something we're going to think about as well. So just to make sense of it, this is when this workflow is applied to the extrusion. We just have the first level exposing robot position, and Grasshopper will monitor that position against the model environment. And if it reaches certain boundaries or conditions that we want, it will trigger the function running on the Arduino. And something that we're very close to also implementing is flipping the protocol the other way, because instead of just reading, we can actually write directly from our parametric environment. So why is this important to have this conversation? We can in order to leave the lab, really, we need to give the robots more awareness, I guess environmental awareness through sensor data, so you can pre-prepare, pre-adjust before it starts to work. Of course, positional awareness will give it the ability to implement collaborative strategies with humans, and fabrication awareness, so self-correct of paths, extrusion rates, and monitor the layers. And right after this, we'll have a deep dive session with Michelangelo. It's not really Michelangelo yet. It's still actually a work in progress. But it's a very simple workflow with parts of what I showed you before. And we'll hopefully make a collective piece that will be preserved after this conference is over. And thank you.